So welcome to the online training session day 2. In this training session I am going to show you the 1D meshing options and the concepts. So the training series details are as follows. We have covered the day 1 session, that is FEM theory. Now today we are going to cover the day 2 session, that is 1D meshing. The topics which I am going to cover is how to create rod element, that is rod element subjected to tensile forcing. We will see one example on this. We will solve the same problem using one single rod element and then solving the problem using 10 rod elements between two nodes for a particular distance. Then we will see the rod element subjected to bending force. As on the theory session I have discussed that rod element supports only 2 degrees of freedom. So we will check what if we apply the bending forces. Then how to create bar elements. So in this I am going to cover bar elements subjected to tensile forces. Then concepts of CDEF point, that is comes under the hyper beam portion that I will show in the HyperWorks tools. Then bar element subjected to bending forces. In the case 1 I am going to use one bar element for the length of 1000 mm and 10 bar elements for the length of 1000 mm and see the differences in results. Then how to create beam elements, that we will see. Beam elements, in this we are going to see beam elements subjected to bending using rectangular cross section. We will use a rectangular cross section, that is a different one. Then the case 1 is when the force is acting on a smaller side of rectangle, and what will be the stresses and deflection or displacement when the forces are acting on the longer side. Then simulation of simply supported and fixed beam problem, that will help us to understand the degrees of freedom, the concept behind the degrees of freedom. And then we'll see how to create 1D elements using other panels like line mesh and other different panels, how to create the geometry, how to create line geometry using hyper mesh, that also we will see. So for most of the linear static analysis or say linear static 1D analysis, we use the formula as MHPCLL, where M stands for material collector, where we define the material properties as steel. If we suppose for steel, material properties as E, nu and rho, which I have discussed in the previous session, the material properties. Then H stands for hyperbeam, where we define the cross section, as we discussed earlier in the previous session, that 1D element by joining two nodes it creates 1D element, but it doesn't understand the other 2 dimensions. So we provide the other 2 dimension, that is the cross section of the 1D element. So we define that cross section using hyperbeam, different software of HyperWorks tools. Then T stands for property collector, where we define the physical properties of element like cross section, area, polar moment of inertia along x axis and y axis, or polar movement also. Then C stands for component collector, where we define the property and material to the appropriate component, where and as in component my geometry and meshing will be there. So my elements are present in component collector, so we define a proper property and material to the component collector so that my elements will get also assigned the component collectors. Then the L stands for load collectors, where we define different load collectors as per our requirement. So let's suppose we want to apply the forces or constraints on my model. So here we define load collector as force and constraints, and then apply using a different panel. Lastly, we define load step, that is here we define the type of analysis which I am going to perform, or which we are going to perform, like linear static analysis, normal model analysis, buckling analysis, and many more. So you define the type of analysis by providing the load collectors in load step. So let's start with the first topic, that how to create rod element. So we will analytically first solve this problem, that is rod element subjected to tensile force. The cross-sectional dia of this rod element is 50 and it is constrained at the one end, as you can see here, and a force of 1 lakh Newton is applied on x-axis. The total length of this rod is 500 mm. The value of E and nu is taken for steel, and the analytical answers has been calculated as the stress value is 50.95 and the displacement or deflection should be around 0.12 mm. So now we will move to HyperMesh or HyperWorks to perform the same analytical problem using FEA and solve this same problem using CAE tool, so that and comparing the results of analytical and CAE simulation. So to start HyperMesh, go to Start, All Programs, Altair HyperWorks, and open. Go to Altair HyperWorks 11 Student Edition and open HyperWorks. Once you click on HyperWorks, it will start the HyperWorks window, as you can see. The default setting allows us to select the user profile. User profile stands for the solver for which you want to create a deck, as HyperMesh is a preprocessor. So you create different decks for different solver. So as in Student Edition, you can create a deck for radios and OptiStruct. So as today we are going to perform the linear static analysis, so we will select the user profile as radios bulk data and click on OK. So it will load all the scripting and everything related to the linear static analysis, that is bulk data format. So once your user profile is set, sometimes this user profile window doesn't appears when you start HyperWorks. So don't worry about it. You can click on this icon, that is load user profile, or go to preferences pull down menu, select user profile, so it will open the same window. Always make sure that this checkbox always show at the startup is checked, so that it will automatically show when you start the HyperWorks. So now to define this problem in HyperWorks, I will go step by step. My first step is to define the material as per NPCLL, as you can see. So first I will create the material. So to create the material, click on material icon. This icon is used to create the material collector. Enter the material name as steel. Define a color. Select the type as isotropic, as in the previous session also we have discussed the different types of material, that is isotropic, anisotropic, orthotropic. So select the type as isotropic. Select the card image as MAT1 and MAT4. So the difference between the MAT4 and MAT1, you can find it out in, if you go to Help, Other Applications, Radios, Motion Solve and OptiStruct. Click on Allow Block Content. Click on Search. Enter here MAT1. When you click on MAT1, it will come up with different options. Select MAT1. So these are the properties of MAT1. Material property definition, Form 1. Defines the material property for linear temperature independent isotropic materials. And for MAT4, if you type MAT4 here, it will come up with the MAT4 definition. Define constant thermal material properties for conductivity, density and heat generation. So, and about if I go to HyperMesh again, select Mat1 card image, because linear static, as I told you, I am going to define the linear static analysis. So I will select card image as Mat1 and click on create edit to enter the other parameters. So so the next question arises is, what does these value means? What are these E, G, new, Rho, A, TREF, GE, ST, SC, SS, and what is this MAT S1, MAT TT1, MAT 4? What are these parameters are? So to know more about it, you can again in the same help file you can type MAT1, select the MAT1 card image, and if you scroll down it will show you that MID stands for here, MET ID stands for the unique material identification number, that is material identification number. E stands for Young's modulus, G stands for shear modulus, nu stands for Poisson ratio, Rho is mass density, A is thermal expansion coefficient, TREF is reference temperature for thermal loading, GE is structural element damping coefficient, ST, SC, SS is stress limits in tension, compression and shear used for composite ply failure calculation, and other comments related to it. So it is stating that either E or G must be specified, that is non-blank. So to define it, the material properties, either you should provide the value of E or G. And if you want to know more about it, you can study this. So I will define the values of E, nu and Rho. By default, HyperWorks fixed the values for steel. If you want to change, you can change it as per the table explained in my previous training session. So the last slide, I guess, contains the values of E, nu and Rho. So you can define them if you want to change the material properties. So I will click return after defining all these E, nu, Rho values. Again I will click on return. Then on the model browser I will see whether my material is created or not. So you can see on the model browser my material as steel has been created. Now as per my formula, my next step is H. So I will create HyperBeam. So to create HyperBeam, I will go to 1D. On 1D I will select HyperBeam. So on 1D page, click on HyperBeam. In HyperBeam panel, select standard section radio button. In standard section, select the standard section library as HyperBeam. There are some predefined shapes, there are some predefined cross sections available in HyperWorks. So you can select any one of them. So as my problem definition is, we have to create a solid circle. So I will select solid circle and click on create. Once you click on create, it will redirect you towards the HyperBeam GUI, as you can see here. And just you need to enter the value of radius. Make sure you enter the values of radius. My dia as per the problem definition is 50, so my radius will be 25. Now here at the right hand side of your screen you can see it calculates the area, moment of inertia, centroidal, then polar moment of inertia, radius of gyration, torsional constant, everything it calculates automatically for the radius 25. And you can rename it also. Say suppose CIRCULR circular section R25. Then to again we'll come back to HyperMesh. So to again move back to HyperMesh, click on model view icon at the top left corner of your screen. Then click return to exit the HyperBeam panel. So on the model browser you can see your beam section has been created. So as per my formula, my material is created hyperbeam is created. Now the next step is to create property collector. So I will create a property collector. So to create property collector, I will click on property icon. This icon is used to create property collector. Select the radio button as create and enter the property name as circular section rod. Define a color. Select the type of the cross property which I want to define. Like I am going to create 1D elements, I will define the property for 1D. I will select the card image as I am going to create a rod element, so I will select the card image as P rod. Also same, if you want to view more about this card images, you can just simply go to this and enter P rod and it will come up with all the properties. That A stands for area of rod, J stands for torsional constant, C stands for coefficient to determine torsional stresses and other things related to the. Then it will ask for the material, so I will select the material and it will ask for the beam section. So I will select the beam section which I have created using hyperbeam. Then click on create edit to see whether it has taken the values required to define the physical properties or not. So yes, it has taken the values of A and J which are required to define the physical properties, that is the cross section of my circular rod. So I will click on return. Again I will click on return to exit the property collector panel. Now on the model browser you can see my property has been defined, circular cross section rod. Now the next step as per my formula is to create the component collector. So to create the component collector, I will click on this icon. This icon is used to create component collector. So I will select the component name as rod element, say circular. Define an appropriate color. Select the property. So my element will get the proper card image of property, that is P rod, and material of steel as mat 1. And then click on create. So on the model browser you can see my component got created, that is rod element circular. Now before moving to the next step, that is load collector, I need to generate the nodes and elements so that I can apply the forces and constraint on that particular node. So now before going further, first I will create the nodes and elements. So to create nodes, go to geometry, nodes. On geometry page, select node panel. In this panel, select the first option and enter the XYZ systems, everything as 0, and say create. Once you click create, it will create the node, but as you can see, it will create the node, but the thing is, it creates the node, we don't know at what coordinate system this current GUI is. So press F from your keyboard so that it will fit to your screen. Then as my distance is 500 in x-axis, so I will enter 500 in x-axis and say create. Again it created the node, but it's not there, so I will click on again F from my keyboard. You have to create F, you have to click F from your keyboard so that it will be fit to screen. Two nodes will get fit to screen. Now by using these two nodes as the reference, I will create an element. So to create a rod element, click on 1D page, rods panel. To create rod element, click on 1D page, rod panels. Select the property that we have created. Select the type of element as C rod, that is component of rod. If you want to see the what is C rod stands for. So you can enter here and select. So rod element connection defines a tension compression element rod of the structural model. Okay. And then select node 1 and node 2. It will create the rod element. You can see here. To view this in 3D representation, as in my previous slide I already mentioned that 1D elements are represented using a line, but in HyperMesh you can see it in a 3D representation. So if you click on this option, that is traditional representation, element representation drop box, and select 3D element representation, you can see the 3D representation of it. If you are not able to see the solid structure, this is the line meshing of this. So click on this to select the shaded element. So in this way, this is your rod element. This is single rod element of length 500 mm. You can see that. So now my rod element is created with a proper cross section. So now I will again make it to traditional mode. Now again I will move it to XY plane and check the presentation. That my next step is to create the load collectors. So now I can apply the forces and constraints on my model, on the elements and nodes. So to define the load collector, I will click on load collector icon. Enter the load collector name. I will enter it as SPC. SPC stands for single point constraints. So in industry, generally people used to call constraint as SPC or MPC, whether you want to apply multi-point constraints or single point constraints. So I will enter the name as SPC. Define a proper color so that I can easily see the colors. I will again show you why I am defining the different colors. If I again move it to traditional mode, here by element colors you can see whether the property is assigned to that element or not, whether the material is assigned to that element or not. So you can see it by color itself. So if you are working on assembly, it will be easy for you to see it by color. So that's why always make sure you assign a different colors on your model for each material, property and component. So I will select the load collector name as SPC and select a color and say create. On the model browser you can see it creates a load collector as SPC. Now I will apply the constraint on this model. So to apply the constraint on this model, go to analysis. On analysis, click on constraint. On analysis page, click on constraint. When you enter to constraint panel, select the node on which you want to apply the constraint. So I want to apply the constraint at the rear end. As you can see in the problem definition, this model is constrained at the rear end. So I will select all the 6 degrees of freedom, that is degree of freedom 1, 2, 3 stands for translation along XYZ axis, and degree of freedom 4, 5, 6 stands for translation along, rotation along XYZ axis. So I am selecting 6, but I suggest you to perform the same analysis back to your home by selecting different degrees of freedom so that you can understand how the degree of freedom works. So just select the degree of freedom 1, deselect all and do the analysis, see how the result deviate, so that you will come to know how these degrees of freedom work. Then my next is to apply the tensile force. So to create the force, I will again create a new load collector as force. Always make sure you create 2 load collectors, one for constraint, one for forces. Then define a different color and say create. Click return to exit the load collector panel. Now to apply force on your model, again go to analysis, force panel. To apply forces on your model, go to analysis, force panel, select the node, select the create radio button, make sure your nodes option is on, select the node on which you want to apply the force, make sure this is the global system toggle is on, that is this system. The magnitude is 1 lakh as mentioned in the PPT or the problem definition. This shows the direction, so the direction is x-axis, and click on create. This magnitude percent shows the size of the arrow. If I increase it, it increases the size of the representation. So it only depends the representing of the force. So force is represented by arrow. So this magnitude percent resembles the size of it. If you toggle it uniform size, so you can make it as 100. Then click on return. So my problem definition is finished. Now the last step is to create the load step so that I can define the type of analysis which I want to perform on this particular model. So to define the type of analysis, I will select analysis. I will go to analysis page, click on load step. So I will enter the name as linear static analysis. Select the type as linear static. Check the box in front of SPC and load. Click on 0 number and select SPC load collector. For force loads, I will select force as the load collectors. These numbers represent the load collector numbers. So you just cross check it whether you have applied or assigned the proper load collectors or not. So SPC is 1, yeah, it is correct. And force is 2, that is also correct. Then click on create. So on the model browser you can see your load step is also created. So before moving further, we will just cross check it whether my MHP CLL, the formula for 1D linear static analysis is completed or not. So material is created, properties MH beam section is created, property is created, component is created, load collector and load step. All these things are created. So M, H, P, C, L, L. Everything is done. Now the next step is to save this file and run the analysis. So to save this file, I will go to Files, Save as Model. Select the destination where I want to save it. So I will create a new folder as training session. First bar element. I will again enter here as bar element. I will enter the name as bar element and save the file. Then go to analysis, radius. To solve this, we will use radius as a solver. So go to analysis, radius. Select the export option to all so that it will, after the solver process done, it exports all the files which are necessary. Then run option to analysis. Sometimes this option is to check the elements quality and whether the model is ready to run or not. So we don't want to check, we just want to run this model. And memory option to default memory and click on radius. Once you click on radius, it will start the solver process and it will show the message as analysis completed. So once this message appears on your screen that analysis completed, then click close window and split the HyperWorks GUI into two to view the results. So to split this HyperWorks GUI into two, click on page window layout drop box and select the two window option. Click on the second window. It will open the HyperMesh GUI. As you can see, the panels are different in HyperView GUI. Click on folder option and select the load model. Browse your file, that is training session 1 bar element. and select the bar element H3D file or HyperView player file. In some systems you will find HyperView player, or in some systems you will find H3D file, or if you are not finding it, both the names, right click on file, you will select the file, you will get the file type, that is H3D. H3D files contains the results, so always select the H3D files. Then click on open and say apply. Once you click on apply, I will click on this expand reduce window icon, so I can easily view the results, as you can see. So these are my HyperView GUI and I have loaded my results on HyperView. Now to view the results of the values of displacement and stress, click on contour, this icon. Select the result type as displacement, keep the magnitude as it is and say apply. Once you click on apply, you can see the displacement is coming as 0.12 mm. I will just cross check it with my analytical solution. So yes, you can see my results of displacement are correct. Now values of stresses. So select result type as element stress, C rod axial stresses because the force is axial, and averaging method to simple and say apply. So as you know, stress is equals to force upon area. So during the axial force along the length, the value of stress doesn't change. Along the cross section, the value of changes. So it is showing me the value of stresses along the length. So you can see that my forces is coming as 50.93. So if you want to see the minimum or maximum value, click on this measure icon. Check the box in front of static min max result of minimum, so you will see the static maximum value is 50.93. In the presentation you can see the value is 50.95. So my analytical and software results are matching exactly the same. But this is in a line mode. If you want to see it in 3D mode, that is solid mode, so go to preferences, options, visualization, bar type, that is a rod element, select rod type as cylinder, apply and OK. So this is the results, 3D representation. If I again see displacement, so you can see this is the 3D representation. So you can view the results in 3D representation also in HyperMesh. So as my results are exactly matching with the analytical answer. Now the second point is solving the same problem using 10 rods. This time I have used one rod for 500 mm of length. Now I will create 10 rods between the length of 500 mm and see how it works or how it differs. So again I will click on this expand reduce window and click on this HyperMesh and again expand this. Go to delete panel and delete the element. Click on the drop box, select the loads and say delete. So I will keep the material, beam section, property, component as it is and delete the load collector as well as load step both. So I will delete both the things so that I will again, after creating the elements, I will create the loads again. So now to create 10 nodes or to 10 elements or 10 rod elements in between these two, go to geometry, nodes, select the fifth option, that is 1, 2, 3, 4, 5, interpolate nodes, select two nodes between which you want to create number of nodes between 10 and say create. It will create 10 equal distance node with the reference of which we can create the 10 different elements. I will show you one more option to create directly elements without creating the nodes. Then again I will go to 1D bars. I will go to 1D rods. Select the property as circular, element type as C rod, node 1 to node 2, node 1 to node 2, node 1 to node 2. In this way I will create the 10 elements between these two. So this is the one way of creating the nodes and elements between two nodes. For the bar element, I will show one more different option available in HyperMesh. Now again, Shift F2, or I will remove these temporary nodes, as I mentioned in my theory session that if you don't want the temporary nodes, just remove it. So to remove it, I will go to Geometry, Temporary Nodes, select Shift plus left mouse button and drag the window and say clear to remove the temporary nodes. If you want to off, you can off this C rod element. It is element info. Then again I will create the load collectors. I will first create force. I will on the load collector, you can see the forces created. Now the analysis, forces. At this point I will create the force. Similarly, I will create another load collector as SPC. Create, return, analysis, constraint, select the node, check all the degrees of freedom and say create. Go to analysis, load step, linear static, analysis, SPC will be SPC and loads will be force. Check the values as SPC is 4, force is 3, that means it is correct. Say create. Then go to file, save as model, 2 bar elements and save. Then I will run this as analysis, radius, and again click on radius. So my analysis got completed. I will close this and split it into 3. So I will click on the third window, click on folder option, click on folder option in front of load model, browse the file and say apply. So this is my file. So I will check with the values for displacement for 1 and 10 rods. So again click on contour and say apply. If I click on static min max, so you can see the value of static maximum displacement is same. And if I click on elemental stresses, C rod axial stress, averaging method to simple, the value of stresses is also same. So for axial loading or for 1D elements, it doesn't matter if you pick 1 or 10 elements. But for bending or torsional, it will affect. Okay. So now I will pick the same model and check what if I apply the bending force on this same model. This is the tensile forces. Now what if I apply the bending forces? So I will just delete this force, or I will update it. I can also update it. I will show you how to update. Go to analysis, forces, update, make this as the current, because force is the current one. Select the force which you want to update, that is load which you want to update. The magnitude we will keep as same, but the axis we will change to y, and in negative y axis, so upside down the force will act, and say update. We will update all the parameters. So now I have applied the bending force. So keeping all the other parameters as it is, so I will save this file, model 3 bar element analysis radius. Again I will click on radius and solve it. Now I will split it into 4. Again click on reduce window, click on folder option, load model folder option, third H3D, and say apply. Now let's check the displacement value. So it is showing very uneven displacement and zero stress value, as you can see. If I on this static min max, so the static maximum value is 0 because it does not support the bending degrees of freedom. That's why it hasn't solved that model. So as I told you in my previous session that rod element supports only 2 degrees of freedom. So this is the analytical solution of it. So in this way I have ended with this first topic, how to create rod element. That is, we have discussed rod element subjected to tensile force, solving the problem using one single rod element, solving the problem using 10 rod elements subjected to bending loading. Now I am going to show you how to create bar elements. So let's start with the bar element subjected to tensile forces. So we will see, we'll use a different cross section here, that bar element is subjected to tensile forces. We'll use a cross section, that is a square section of 100 by 100 mm. The length will be same, that is 500 mm, and the tensile force is also same, that is 1 lakh Newton. The value of E and U is also same for steel, and then we will see for analytical solution the value of stress should come as 10 Newton per mm square, and the value of displacement should come as 0.024 mm. So now let's see for this. So I will quickly make this as new. And again turn it back to 1. So again for the bar elements I will follow the same process. First I will create the material as steel, define a color, type as isotropic, card image as mat1, click on create edit to enter the values of E, nu and rho. Then click return to exit the material collector panel. So in this way you can see material is defined. Then I create property. So property is, before creating property I will create beam section, that is MH stands for hyperbeam. So go to 1D. In 1D I will click on hyperbeam to create a beam section. Select the standard section library, the third radio button, standard section library as hyperbeam. But this time I will select solid rectangle as I am going to create square section. So select solid rectangle and click on create. Enter the dimensions as 100 and 100. So it will calculate all the values as area, centroidal, moment of inertia, and everything it calculates automatically. Again move back to hypermesh, that is by clicking on model view. Click return to exit the hyperbeam panel. You can see your beam section has been defined. Now click on property icon, the property collector icon. Enter the property name as SQUARE a square section. Define the color, type as 1D. Card image this time as P bar, because we are going to create the bar element, so we will define P bar. Material as steel, beam section as auto section 1, and click on create edit to check whether it has taken the values of area, polar moment of inertia or torsional moments. Then again click on return. Then I will create a component. On the model browser I can see property is created. Now I will click on component, bar element, square section, define a color, define the property and say create. So my component is created now. Now the next step is to create the geometry. So I will go to geometry, nodes, select the first option, 0, 0, 0, create, press F from the keyboard. And 500 nodes 0, 0, 0 and say create. So go to geometry, nodes 0, 0, 0, create, and 500, 0, 0, create. So in this way I have created two nodes. So now I will create a bar element. So 1D bar, select the property. To create the bar elements, go to 1D page, bar panel. Same panel is used to create the beam elements also. So 1D bars, property, select the property, element type as C bar, that is component of bar. Select the orientation perpendicular to the length of the element. So you don't select the orientation axis as X. Apart from that, you can select any other axis. So I will select Y axis. Select these two nodes. So you can see, as I can tell, I already told you that this is the line element. So you want to see the shaded geometry, shaded mode. This is the shaded mode. Click on this icon to enter to shaded mode. So this is the square section bar element. Again we will follow the same process. Create the load collector as force. Say create, analysis, forces, 1 lakh in x-axis. Pick the node, say create. Load collector SPC, define a different color, create. Analysis constraint, constraints all the degrees of freedom and say return. Then analysis load step as bar element, linear static, SPC and load, SPC as SPC, load as force, say create. Save the model. Fourth bar element, and analysis radius. Select the export option to all and radius. So this will solve this model. My model is solved, analysis completed. Go to HyperView GUI, split this window. and open the file, say apply. The displacement, say apply. Measures static mean max. So my maximum displacement is coming as 0.024. On the presentation you can see the maximum displacement is coming as 0.024. Now we will check for the stresses. So elemental stresses, C bar, C beam, longitudinal, apply. So you can see my maximum stress is coming as 10, which is same as here. So the tensile force results are exactly matching. So now we will move towards the next, that is concept of CDEF point. In hyperbeam, you have seen this cross section, the square cross section as I have created earlier. So this is y-axis, this is z-axis. So HyperWorks create CDEF 4 points on which it will calculate the results if you define those 4 points. So to define these 4 points, you have to define the 2 coordinates, that is y. Point C coordinates will be y and 0, D coordinates will be 0 and z, E coordinates will be minus y 0 and F coordinates will be 0 z. So for a square section of 100 by 100, the C point will be 50, 0, D point will be 0, 50, E point will be minus 50, 0 and F point will be 0, minus 50. So if you orient the hyperbeam y-axis with the global y-axis and apply bending force in negative y direction, then your C point, this y-axis, you apply with this y-axis, orient them. So your C point will be in tension and showing positive stresses, and E point will be in compression showing the negative stresses. Whether the neutral axis, that is the z-axis, will point, that is D and F, will show the 0 stresses. But if you orient the hyperbeam z-axis with global y-axis, then your D point or E point will show the positive, your D and F point will show the positive and negative stresses, where the point C and E will show the 0 stresses. This thing I will explain you in this example while I will orient them, and how to orient them using different orientation and what is the results of CDEF point and how to assign them. I will show you in this example that this is the same bar element. I am applying the forces in bending, everything else is same, and we'll check the results for stresses and displacement. So we'll check that. So I'll again move to hyperview. I will magnify it, keeping all the parameters as it is without changing it. Or what I'll do, I will again create it so that I can make you understand the hyperbeam options. So that it will be easy for you to understand the hyperbeam concept. So I will create the material as steel. I'll quickly go with the MPC process. (1D) hyperbeam solid rectangle. So here you can see it creates the cross section in YZ plane. You can see this. So I will orient this y-axis with the global y-axis. So my point C and E will be showing the stresses. We'll check it. Property, square section, 1D, card image, P bar, material steel, beam section, auto standard 1, create edit. Now we have to input the coordinate systems, that is CDEF points coordinates we have to input. So to input these values, we have to check the box count 1. Always make sure to check this box count 1 to values, input the values C1, C2, D1, D2, E1, E2, F1, F2, so that you will get the stresses on these points. So my C point will be Y0, that is 50, 0, D point will be 0, Z, that is 0, 50. E point is minus 50, 0, and F point is 0, F2 is minus 50. Then I will click return. Again I will click return. I have defined this CDEF point. Now I have defined the component, that square section with a property, square section, and say create. So my material, beam section, property and component has been created. Now I create the nodes, that is one is at 0, 0, 0, another one is at 500, 0, 0. Go to 1D, bars, select the property, C bar element type. I am orienting it with y-axis, so my point, the stresses will be at point C and E. D and F points will have to have the 0 stresses. We'll check it. Then create the load collector as force, create, go to analysis, forces, select the node on which I want to apply the force, select the magnitude. The magnitude is same, that is 1 lakh, but in negative, y-axis, and say create. Now again I will create the SPC as the load collector to define the constraint. Say click create and click return. Go to analysis, constraints, select this node and say create. Now I will save this file, 5 bar element. Go to analysis and radios and solve this model. Oh, I haven't defined the load step. So I will go to analysis, load step, select SPC as SPC, load as force, and say create. Save this file, analysis, radios, and I will run this file. So my analysis is completed. So I will split this into 2. Click on open folder, browse the 5th one and say apply. So my displacement value, if I measure it, it should come as 2.318 as per my hand calculation. And the value of stresses, if I click on the contour plot, you can see here C bar, C beam, longitudinal stress, SAC, SAT, SAE and SAF. So C point, if I pick on the C point, it will show me the stresses as 300. If I pick the D point, it will show me the 0 stresses as it is a neutral axis. At E point, it will show me again the negative, that is compressive stresses. At F, it will show me again 0 stresses. So now you can see this results. Okay. Now what I will do now, I will change the orientation and again solve it. So I will go to 1D, bars, update. I will pick this element, select the property, select element type C bar and change the orientation to Z. Now I am orienting global Z axis with Y axis. Currently I am previously I have oriented global y-axis with the hyperbeam y-axis, but now I am orienting global z-axis with y-axis. So if I update it, I will update all these parameters. As it is a square, the values of stresses and displacement will not change, but the answers on CDEF point will get changed. Now the stresses which I will get will be on some different points. So I will again click on model, save this, click on save, analysis, radius, solve this model. Now I will split this into 3 and say apply. Now here you can see, first I will check it here. At point C, it is giving me the value 300, but the same, if I select at point C, simple, and apply, if I click on measure of the minimum, it is same point, it is showing me 0 as I change the neutral axis. So if I change it here, the point D, it is showing me the negative 300 stresses. So my neutral axis has been changed. At point F, it will show me the positive value. But the question arises, the stress along the length should also vary. It is not varying, or at least it should show some color change. The stresses at the corner is maximum, but it is still not showing because it's a single element. That's why it will show the stress values at 2 nodes only, because it calculates the values at the nodes, as I told in the last session. So what I will now create, I will create some more elements in between these 2 nodes. So I will go to delete panel, also delete the elements and loads. Earlier I have shown to create 10 nodes and create the elements. Now I will show you one more option available in HyperMesh to create few more elements in between these 2 nodes. So go to 1D, line mesh, to automatically create n number of node elements directly by choosing 2 nodes. From the drop box, select nodes, pick these nodes. From the element configuration, select bar 2, select the element size, say 50, and keep select the property which we have selected as a square and say mesh. So it will create 10 elements, say return. Remove these nodes that I don't want. Now we will apply, or we will create the forces. So as the bolt collector is the current collector, so as SPC is the bolt load collector, so SPC is the current one. So I will first apply, create the constraint on my model. So go to analysis, constraint, and say create. Then I will make this as the current. Go to analysis, forces, keep this all the parameters as it is and say create. I will just update the load step with SPC and force and say update. Now I will save this same file and run the analysis and see the results. So now I will split it into 4. So now we will see the values of stresses and displacement. So the displacement will be same, the values will be same, but the representation will be different. And about the stresses, if I select the result type as C, simple apply. So now you can see there is a color change. So now it is showing from positive to negative. On each element it is calculating the stresses, bending stresses. So the bending stresses will differ if you increase the number of node elements. because it does not, it depends on many other factors. As you can see, it depends on M by I. So bending stresses changes as the length changes. So that's why it will show the difference. As you can see, if I again click on measures and on the minimum, so you can see the minimum stress to the maximum stress at point C, and at point E if I click, the same values goes for the negative. If I see the animation, you can also see the animation. Go to deform, and increase the deform value. So now you can see this is the, in this way this bending is going to happen. So the maximum stress will be at the corner and the minimum stress will be at the tip of the bar element. Okay, so I will pause this. I will click on new. So again I will move this. So in this way I have entered with the bar element subjected to bending. Now the next topic is to how to create beam element using rectangular cross section. So the next topic, we have entered with the second topic, that is how to create bar elements. How to create bar elements, where we have discussed bar elements subjected to tensile force, concept of CDEF point, bar elements subjected to bending forces. First case when I use 1 bar element, then the second case when I use 10 bar elements. What is the difference between 1 bar and 10 bar elements? Now we'll move to how to create beam elements. So for the beam element, I'm going to use this case 1 and case 2 when I change the orientation for the shortest distance, that is 50 mm, and for the longer distance, that is 100 mm. When I apply the forces, same force, everything is same, but the cross-sectional length changes. So it will change the values of stresses and displacement because I changes. If I get changed, the value will also get changed. How to simulate these two cases and how the orientation will affect the results. Now let's see that. So again we'll follow the same process, MHPCLL sorry, and create two different similar cross section but orient them differently and check the results. So it will help us to understand the orientation of the hyper beam with the global axis. So I will quickly go with the material, say create E new row, go to 1D hyper beam. I will use the solid rectangle and click on create. I will change the parameters from 100 mm and 50 mm. So this one I will pick it as 100 and this I will pick as 50. So my y-axis length is 100 and x-axis, z-axis length is 50. I'll again go to hyperbeam to explain the CDEF point. Now the CDEF point, I will explain what to enter the CDEF point. This is C, D, E and F. So if this one is 100, so my C point will be 50, 0. My D point will be 0, 25, as this one is 50. Similarly, this will be minus 50, 0, and F point will be 0, minus 25. So I will enter the CDEF point in this way. So again I will go to Hyperview, click on Property, rectangle section, enter the property name, color will define it 1D. We'll use CP beam this time as the property type, material as steel, beam section as auto section 1, and click on create edit. So it will, by default it takes the values of A and other parameters, like I can, if you want to see the beam, if I click here, you can see that L1 stands for area moment of inertia in plane 1 about the neutral axis at end A, and L2 stands for area moment inertia in plane 2 about neutral axis at end A. J is torsional stiffness parameter at end A. So these other parameters to define the cross section, it takes automatically. So I will check the box continuation line 2 to input the values of C1, C2, D1, D2, E1, E2, F1, F2. So C1 is 50, 0, D1, D2 is 0, 25, E1 is minus 50, 0, F1, F2 is minus 0, minus 25. So I will click return. Again click return to exit the property panel. So in this way you can see my material, beam section, property is defined. Now I will define the component, that is element, beam element. Define a color, select a property and say create. So my component is also got created. Now as per my case, I will create the element length of 500. So I will create two nodes. First I will create at 500, second will be at 0. Using the same panel, 1D line mesh, I will create 10 nodes in between, but this time I will select the bar configuration as bar 2, property as square section, and say create and return. But this option will not allow me to orient them properly. So as per my wish, I cannot orient them. So what I will do now, I will delete these elements and move to the traditional way of creating the elements, that is creating by nodes. So I will go to geometry, nodes, click on the fifth option, enter the value as 10. From this to this I will create the 10 nodes. Go to 1D, bars, bar 2 panel, select property as rectangle section, element type as C beam because I am going to create beam elements. I will orient it with y-axis first. I will make it in a traditional mode. Or to understand you better way, I will just delete this and create one more element with a different orientation, and then I will show you. So you can see, if I change the orientation, when I orient it with y-axis, the hyperbeam y-axis is oriented with this global y-axis. So that's why the length is coming as 100, which I have defined. But when I change the orientation to Z, so my y-axis of this hyperbeam get oriented with the global z-axis, and the beam section is coming as like this. So always make sure the orientation should be proper on which you are going to apply the force. So you have to know that on which side the force is going to apply, on the smaller side or on the longer side if the cross section is not symmetric. Okay. So we'll check the results. So I will delete this element. So again I will pick y-axis orientation. So my elements got created. Now I create load collector as SPC, analysis, force constraints, fix this, and then I will go to forces panel, create, analysis, forces, negative y direction, the same force I will apply, and then define the load step, beam analysis, SPC as SPC, load as force, create. Now I will save this file, 8 beam element, go to analysis, radius, split it into 2, click on open folder, browse the folder, H3D file, and say apply. I will check the displacement value, the static minimum maximum. I will off the minimum. So as per my calculation, the displacement is coming as 4.7 and the stresses is coming as 600. So the orientation, you can see if you orient it with the y-axis, the analytical and these answers are matching. Now instead of creating the new one, I will just simply update the existing elements. So to update the existing 1D element, go to 1D, bars, update, select the elements and change the orientation. Select the property, element type C-beam and click on update. So now I will just first move into traditional. So this is the orientation. Once I click on update, you can see the orientation is changed. Now I will save it in a different folder to compare the results. Go to analysis, radius, split it into 3 windows, folder option, browse the last folder and say apply. So the displacement value is coming as, you can see, 19.17, that is exactly the same one, and the stress values at point D, sorry, at point F will be 1200, which is matching the analytical answers. So in this way, the orientation is very important. It will affect the results. If you are using a cross section in which the dimensions are different, if you are using the same dimension cross section, that is square or circle, then the orientation will not play a major role. But if you are using a cross section as a rectangular I section or L section, then the orientation play a very important role. So in this way, we have ended with this thing. Now I will show you the effect of degrees of freedom in the analysis. If I off or on the degrees of freedom, what will be the effect in the results? So to understand that in much better way, we will use popular examples of fixed beam and simply supported beam. There is a very little difference between these two. Is if we put it in a ZXY plane, so if we fix all these, that if it's a fixed beam example, then all the degrees of freedom are fixed. But if it's simply supported beam example, then the rotation about z-axis has to be free, because it will not provide the reaction for the rotation about z-axis. So this is the only difference between the fixed beam and simply supported beam. So we will see the analytical results are here. So we will solve the same problem using HyperWorks tools and check for the results, that what are the results are matching or not. So instead of creating everything from the scratch, that is material property, component, elements, I will use the previous model, that is actually this is the circular one, so I have to create it. Okay, I will create it. So I'll create the material as steel, E new row, 1D hyperbeam, solid circle, create. The dia is 100, that means the radius will be 50. Creating the property circular, type as 1D, card image P beam, material as steel, auto standard 1, count continuation line 2, 50, 0, 0, 50, E value is minus 50, 0, 0, minus 50, and return. Again click return. Then component, beam element, or I will name it as fix beam, property as circular, say create. Go to geometry, nodes, the distance here, the distance is 1000 mm. So option this, 0, create. Then I will define geometry, nodes, create, and this time instead of 500 I will enter 1000. So my 2 points are created. As it's a circular cross section, so it hardly matters with the orientation issue. So I will use 1D line mesh model, say element size to 50, select 2 nodes, element configuration to bar 2, select the circular property, node 1, node 2, and mesh. It will create the elements. I will clear the temporary nodes and create the force load collectors as force, create, analysis, forces. The force has to be applied at the midpoint of 30,000 Newton. So I have to first find out the midpoint. So we go to geometry, distances, 2 nodes, from this node to this node, node between. So this is the midpoint. So I will go to analysis, forces, pick this node, 30,000, or it's minus 30,000 in y-axis and say create. Or it may be possible if it's not applied on the that particular element. So what I will do, forces create, and then again I will check whether it is a midpoint or not. So geometry distance, because sometimes it creates on temporary node. So yes, it is on the midpoint. So I find it out the midpoint and then apply the force on the elemental node, not on the temporary nodes. Then my next step is to create SPC, that is constraint. Create. So now here you can see analysis, constraint. First I will analyze it for fixed beam. So I will constrain all the 6 degrees of freedom. Go to load step, fix, linear static, SPC as SPC, load as force, and say create. Go to file, save as model, select 10, fix beam, analysis, radius, export option to all, and click on radius. This will solve this model. Go to split this window and go to browse the file and say apply. Same as we done earlier. Check the displacement. So you can see the displacement value is coming as 0.163. That is same as the fixed value. And if we go for the elemental stresses, the value is coming as 38.19. So it's showing the results for fixed beam, because I have constrained all the 6 degrees of freedom, that is 1, 2, 3, 4, 5, 6, translation along x, y, z and rotation along x, y, z. Now I will use one more case where I remove the 1 degree of freedom, that is 6th rotation about z axis, and then view the results, how it behaves. So I will go to analysis, constraints, update, select the load I want to update, just of the degree of freedom 6, and update it. Keeping all the other parameters as it is, I have just removed the 6th degree of freedom, that is rotation about z axis. Then I will save this file as 11 simply supported beam. Save. So analysis, radius, split this window into 3, and say apply. Again go to XY. If I check the displacement value, you can see the displacement is coming as 0.61, that is for simply supported, and the elemental stresses are coming as at point E is coming as 72.59. The maximum stresses that will be at the center. So in this way, the degree of freedom affects the results. So if you on or off the degrees of freedom, the results will vary drastically. The analysis concepts will change drastically. If you on 1 degree of freedom or you off 1 degree of freedom, the problem definition changes from fixed to simply supported. So now I have completed the create 1D elements using other panels like line meshing and all. Now many times students or people ask me that apart from creating rod element, bar element, beam element or these examples, is there any other problem or any other practical problem which we can simulate using 1D element? So yes, we can, and I'm going to show you one more problem which I will create the complete model using HyperMesh and solve it for modal analysis just to check the free run. This is not for the analysis, this is for the meshing purpose. So I will show you how to create some structures, what are the different panels available in HyperMesh and how you can create a structure and how you can mesh a structure at once using options, 1D meshing options available in HyperMesh. So let's start creating a roll cage structure in HyperMesh itself and then doing the meshing of on that roll cage structure at once and then just performing a free run to check all the elements, criteria, material properties, loading conditions, everything, the meshing connectivity. We'll just perform the free run. So this tutorial is not for the analysis point of view. This tutorial is for creating a geometry in HyperMesh and doing the meshing, 1D meshing at once for an entire structure. So I will start with creating nodes. So I will first create 0, 0, 0 node. Then let's say 300 by 300. I'm taking arbitrary values to define a square section. So this is the front side of my roll cage structure, as you can see. Now I will drag this somewhere to a length of, let's suppose, 250 mm. So I will use some shortkeys available in HyperMesh to increase the speed of your modeling or meshing. So press Shift F4 from your keyboard to enter to translate panel, or you can go to Tools and Translate panel. This is the same panel. So the first shortkey is press Shift F4. Select the nodes, click on the nodes, say duplicate. I want to translate it in Z-axis in the negative magnitude by suppose 250 mm or let's suppose 400 mm and say translate negative. So in this way I have created a box. Now by using these nodes I will create a line structure. So I will go to geometry, lines, select the second option, that is linear nodes. From this node to this node I will create one line. From this node to this node I will create another line. So in this way I have created a front box structure for my roll cage. Then I will drag it a little more towards the back. So I will again press Shift F4, select these nodes, say duplicate. Let's drag them to more distance of 600 mm. And along with that we will drag these nodes somewhere to height of 300 mm on y-axis I will duplicate it, otherwise it will drag the same. Then again I will create, go to geometry, lines, and again I will create the line structure. So from this to this, create, this to this, create, this to this, create, from this end to this end, create, 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 this to this, create, this to this, create. Now these are about the straight lines. What about if I want to create a circular hoop here? So yes, you can create it. For that, press F4 from your keyboard to enter to distance panel. Pick a node in between these two. Go to geometry, lines. Select the fourth option, arc, center and radius. Select the center of it. First check the distance of these two. This is coming as 150. The radius. Along z-axis we will create this. So the radius is 150 and angle is 180 degree. And I will say create. So in this way you can create a circular loop. Now again press Shift F4 from your keyboard. Nodes, duplicate along z-axis. Again 250 mm. Translate them back, or say 500 mm translate them. Go to lines. From this node to this node, create. Say reject. Second option, create. From this node to this node. If you press the scroll button, it will hit the existing option. So this to this, create. This to this, create. This to this, create. Now from this end to this end, and this end to this end. So in this way my roll cage structure is ready. If I want to create some cross members, also I can create those. So in this way I can create some cross members. As per my requirement, I can create the cross members, as you can see. Now if you want to create here as a cross member, so just select from this node to this node and pick a node between, and again from this end to this end create a line. So in this way you can create a complete roll cage structure by changing the parameters. So this is my roll cage structure is ready, so I will clear the nodes. If to view it better, I will just change the color. So this is my roll cage structure, as you all can see. Now I will do the meshing for it. So before the meshing, I will go for MHPCL, sorry MHPC, not L. So material as steel, create E new row. Go to 1D, hyperbeam, standard section. As I already told you, I am going to create the hollow circular pipe. So I will select thin walled tube and say create. Outer radius, let's suppose 12.5, inner radius is 11. Then properties, circular, 1D, card image as P-beam, material as steel, beam section as auto standard 1, create edit and checking all the values as it is correct. Then go to component, but on the model browser you can see your component is already created. So you just rename it as say roll cage and update with the proper property. It is not, there is no property assigned to it. So just update it. So now the property is assigned to it with material and beam section. Now I will show you how to mesh them all at once. So to mesh them all at once, go to 1D, line mesh. Instead of nodes, select lines, element configuration bar 2, property as circular, element size say 10, and pick all the element lines from dragging it, shift plus left mouse button, click on mesh and say return. This icon is used for geometry on and off, and if I click on traditional, so you can see there are some lines are coming. So these are the line view. If you want this is the solid view. So I will mask one element and I will show you how this is a hollow circular pipe. So this is the hollow circular pipe. Okay, but there is a problem that some of the beams are not getting connected or not getting proper cross sections. If I on this, so you can see 1, 2, 3, 4, 5, 6, 9, 10, 11, 12 lines doesn't have the element showing this cross section. But the meshing is done. If I off this, if I go to mask and mask these elements, I have selected mask, so these elements are there with this line, but it is not assigned with the proper cross section. So to assign them the proper cross section, we will assign them the proper cross section, otherwise it will show an error of the orientation. So the orientation is not proper just. So go to 1D, bars, update, arbitrary select some elements so that once we move into traditional one, so that we will come to know that what are the elements which are not having the proper orientation. And then we will move it to traditional one and off the geometry. So these are the beams. So I will select them from this end to this end. So in this way, you need to just update them with the orientation. Many software doesn't show this orientation problem, but all the software gets this, but they just ignore it. But that is very important to have the proper orientation, as we have seen in my earlier session, that if the orientation changes, the results also get changed. So that's why it should get the orientation. If it doesn't, if it's not getting the orientation, that means there is something wrong, and which may lead to unrealistic results. So always check for the orientation, and if it's not proper, you can update it by using 1D bars panel. So I will select all the elements one by one. So in this way I have selected all the elements. Now I will orient them with y-axis, property circular, element type C-beam, and update all the parameters. Again I will check with the 3D representation. Now you can see all the elements are perfectly fine, have got all the proper orientation. Now I will quickly go for the free run to check whether the quality of the meshing is proper or not, or all the beam sections are connected or not. So create EIGRL. That I will explain what is this EIGRL card is, and when I will go for the analysis session. So I will enter the values of V1, V2, that is initially 1, maximum frequency as 1000, number of modes to 10. In details I am going to explain this in the analysis webinar. So analysis, load step, free run, type as normal model, checkbox of method structure, EIGRL, create. Save the file, say 12 roll cage, So analysis, radius, so I will split it into 2. Open the roll cage data and say apply. If I maximize it, so you can see this is the 3D roll cage data. Eigen modes, if I am on the animation, and increase somewhat deformation, so it will show a larger deformation. So it will be easy for me to see the connectivity. So in this way you can see the different mode shapes, and all the beam sections are properly connected. There is no connectivity issue. If I off this, I will explain you what is this mode functions and mode shapes are. So I just show you how to do 1D meshing, or if you want to perform a bigger model analysis using 1D meshing, how you can do that. Or also you can create the geometry in HyperMesh. That is also possible, how you can do that also, that I have shown it. So in this way I have ended with this session. Thank you very much for attending this online training session day 2, in which I have covered 1D meshing. To improve this online training session, please help us by sharing your valuable comments, and if you like some points or some topics, then also please let us know about it. So at edu-support@india.altia.com. Your comments will definitely motivate us to help an engineering community much better. Thank you very much for attending this session.